Hello. I'd like to talk to you today about Introduction to Tensor Calculus, Relativity, and Cosmology by Lawden. This is a fairly good book for learning tensor calculus, which for a lot of people is a fairly obscure subject. I know physicists might not think so, but the rest of the world probably does. Tensor calculus shows up in relativity, obviously. It also shows up in elasticity. It shows up in crystallography and some other places like that. And I have other books that deal with it in those particular fields, in more condensed matter fields, because that's where I did my research. I did more with that. However, when people come to me from the show and ask me, well, what do you think somebody wants to learn about tensor calculus, what book should you use, I usually go with this one. It's pretty good. I've gone through it fairly recently myself, definitely within the last 8 years, probably within the last 6. And I've even worked many of the problems. I haven't systematically worked the problems. This one has a few too many problems to work all of them. You could, but you probably will get bored because you'll have figured out the issues before you get done with the list of problems. So it's not one of these books that has 8 or 12 problems, and so they're all really important. Instead, it has a few problems, and you just work as many as you can. This one has around, I'm going to say, 30 to 40 on average problems per chapter. And that's a little much. So you have to pick and choose. So, as I said, I like this book for tensor calculus. It's pretty well presented. It is very mathematical, right? There's not going to be a page without tensors on it. So I hope you enjoy them. But that's the reason why you're going to this book, right? You're trying to learn something about tensor calculus, general relativity, and cosmology. Actually, this book has a big section on special relativity, and we'll talk about that in a second. So it has a good explanation, at least as far as the explanations are concerned for tensors go. Let's see. It's also a Dover book. That's also good. It makes it cheap. And this book is fairly similar in its approach to the parts of this book we got through when I was in undergraduate, and I took this undergraduate general relativity course over the summer. So it has a fairly similar method of teaching it. I think if you look at the MIT OpenCourseWare relativity thing, it's a similar approach. And so you can see sort of what it looks like from that. Although that is a graduate class, and I'm not sure exactly how much mathematics they were supposed to come in with. So they probably do a little bit more relativity compared to just tensor calculus than my undergraduate class did, because it was a special topics class and all you needed to do was pass physics 2 to get through. So you'd have physics 2. That means you probably only had calculus 2, and you have a limited amount of time. You have to go through all of this math for something like a Christoffel symbol to make any sense. And they're very important. They're critical. In fact, they're critical. So I did like this book, and let's just look at the index. Table of contents, excuse me, not the index. So, in the table of contents, see we have 7 chapters. Chapter 2, 4, and 2 and 5 are just completely mathematical. And if you haven't seen some of this stuff, a lot of it, the rest of it's going to seem like math. But, it's fairly good. So when we start out, we're starting off with the special principle of relativity and the Lorentz transformations. This is obviously what you're probably looked at in a modern physics course, starting with Newton's laws, the covariance of the laws of motion, the special principle of relativity, Lorentz transformations and Minkowski space, the special Lorentz transformation, Fitzgerald contraction and time dilation, and space-like and time-like intervals, and the light cone. These are all very important. Covariance is very important as well. Covariance basically covariance is a term that's important when your axes don't align. When you do a transformation where rather than like a rotation you have something, you have your x and y axis like this, and you just rotate it. You don't have to worry about if something's a covariant or a contravariant vector in that case, because basically you're just rotating. Everything stays the same. You're not doing anything strange that is going to change how you measure something. However, if you are dealing with special relativity, then if this is the original rest frame, or this is let's say this is the rest frame, and you have another frame in here, then you're going to measure. You've changed this angle between the two different axes, and now how you measure is going to change. In this particular case that I've done, I think this is equivalent to like a Minkowski diagram, and in that case you've got a contravariant vector, which means you measure distances sort of parallel to the axes. Well, that is, your lines are parallel as you mark them off on your axes, your grids. And if you were to do a contravariant instead, or a covariant instead, what's going to happen is you measure perpendicular to the axes. And that's also important. So covariance means you measure perpendicular to the axes after you've done this transformation, right? So you measure your lines your grid lines come perpendicularly out of your axes, whereas in the other ones your grid lines are parallel to the axes for the contravariant. The special principle of relativity, that's obviously critical. This is something we start off with. This is basically what we're going to start off relativity with for special relativity. You're going to swap out absolute space for constant speed of light, and that's going to give you the special principle of relativity, which basically says that the speed of light is constant for everyone. And then as a result, you're going to get your Lorentz transformations, which are true for this Minkowski spacetime, which is your flat spacetime from general relativity. This is the limiting case of general relativity when there are no massive bodies. And then we're going to talk about space-like and time-like intervals in the light cone. These are going to be the things that are going to tell you what a particular observer can influence, right? You can only influence things in this absolute future or this absolute past from you right there. And these things out here, here he's calling them the conditional present. I've seen people call it know where and know when. It's not really a great way of saying it, but that's what they said in that philosophical cosmology course I took. And so that's your conditional present, right? That's the place where things that you can't influence and can't influence you right now are. Let's see. Then we go on from this special principle of relativity chapter to the orthogonal transformation and Cartesian tensors. These are fairly simple ones. These are just the flat sort of transformations, repeated index summation notation. This is very important when you're dealing with special relativity, or relativity in general relativity. Often you'll have something like this, where you'll notice this A has a subscript L and B has an L. What you're supposed to do is imagine that there's a summation for the L in this, and there's also a K between this first A and this U. Again, there's a second summation because there are two repeated indices. That can get you if you're not looking for it, if you're not used to it. If you're coming from somewhere else and then all of a sudden you go to a place where they're using this summation convention, that can get you. And that can make things look really, really weird. But basically, if you were to look at, say, a scalar product with that notation, it's not good if I'm touching this with my, and I do not see anything to write on. So I've only got pens, it looks like. So this is your dot product. If you remember, A dot B is equal to something. That would be the sum over the index I, AI, BI. The summation convention would just write that as AI, BI. So this is not going to be the just one of these terms. It's going to be the sum of all of those terms. And this is just what you have to deal with if you're reading something that uses that particular convention, which a lot of these, especially older books, do. But I mean, it's just to get rid of all these sigmas when you have lots of indices that are being contracted like that. That scalar product is something that they call a contraction. It's one view of it. Another kind of contraction would be a matrix product when you have two matrices, two square matrices multiplied by each other. Then we go to Cartesian tensors, invariants, gradients, and derivatives of tensors. Very important. Invariants are something we use a lot in gravity. Contraction, scalar product, divergence. I was just talking about what the scalar product is. You'll notice here that they have the scalar product and the divergence, and if you come down here, they have the vector product and the curl. They do them. He does them both at the same time. Lawden does them both simultaneously. So you've already talked about your derivatives of tensors. The divergence is basically a scalar product with this del symbol, which is your x derivative in the x direction, your y derivative in the y direction, your z derivative in the z direction. So you just take the first of those two objects and you use the del symbol, and there you use that ddx x hat plus ddy y hat sort of thing, and put them in there. And that gives you your divergence and your curl. This is a very mathematical way to think about it. In that mathematical way, it's very simple, right? When you're trying to understand what a divergence is, when you're trying to understand what a curl is, it's a little more complicated than just the mathematical way of doing it, right? And you've seen that in electricity and magnetism, right? The divergence basically tells you where the sources are. Your divergence is related to your sources, right? Kind of continuity equations, things like that. And your curl is related to how much rotation there is in your field. So these are very important for fields, obviously. Pseudotensors are in there. Pseudotensors are something like the cross product. It's something where when you do your transformations, there's a bit of a difference than you'd have with your normal covariant vector. So they're a little bit different. You don't have to worry about them very much. When you're taking these cross products, you don't have to worry that it's a pseudotensor or a pseudovector, or I've also heard it called an axial tensor, which is a little more meaningful, right? If you have your two axes like this, you have your cross product between them, it's this blue thing here. Then this direction here is basically the direction of your cross product, right? But it's sort of like I'm going from here to here sort of deal. And so we're rotating this way. This is the direction around which we're rotating, the blue pen. That means that the cross product has some different properties from your normal tensors, from your normal vectors, because basically it happens twice, right? So each of those vectors transforms, and so then you do the product, and that means your product doesn't transform in the same way. You could think about it as you square the transformation, and you get a, where you might have a negative sign, you get a positive sign, sort of idea. Special relativity mechanics. We get a second dose of special relativity. All of these things you normally have in the curriculum, or at least in the books in the curriculum. You don't always get to them in the actual classes. So a lot of these things will be new, even if you've taken modern physics, even if you've taken electrodynamics, even though a lot of these things in this chapter and chapter 4 are actually in those books, usually. Not always, depends on the book, but usually they're in the book, usually in the last chapter, usually saying, okay, well, if you've gotten this far and you still have time, now you can look at it. Sometimes not. Sometimes people put some of these things, especially in electrodynamics, up a little closer. So you talk about the velocity vector, mass and momentum, how that's working in special relativity. This is one tensor. The force vector, energy. How does force work in special relativity? Because it still works. That's the whole reason why you're using special relativity, is so that you can use mechanics in this place where the principles of space and time are slightly different, this special relativity principle. Later on it gets even weirder. Lorentz transformations for the force, fundamental particles, so we're getting a little bit of physics in there. Lagrange and Hamilton's equations, so now you're looking at that with special relativity. A little bit more than what you probably looked at in your junior level mechanics course, if you've had that. Energy momentum tensors, which you need to figure out about. The energy momentum tensor for a fluid and the angular momentum. In a way, this means this is something you have for a field. If you have this field and you can construct this energy momentum tensor, you can see how the field's going to push things around. That was one of the things that I thought was so good about the Schwartz electrodynamics book. Yeah, here it is. And I talked about this one earlier by Melvin Schwartz, where he talks about this energy momentum tensor quite a bit in the context of electrodynamics. It doesn't really have very much to do with relativity at all, but it does have its important place in electromagnetism. Special relativity electrodynamics. Now you've got your 4 current and your 4 potential, right? So that the 4 current includes charge as well as your current, right? So that's all part of the same thing. And you know, if you can, there's actually something interesting about this that I should have looked at before if I wanted to talk about it. If you can, sometimes it's possible to get all of your currents to disappear in one frame of reference. So you can do a Lorentz transformation to a place where your 4 current density only has a charge place, only has a zeroth component or a fourth component. I don't remember which one it was in this book. So that's basically what it's saying, is that current and the charge are basically the same thing, and you already knew that, right? You already knew that current is just moving charge, so it makes sense that if you're changing your frame of reference, you could change your frame of reference for current to something where there's no current, and it's just the charge is sitting in place, right? That's very important for understanding how electricity and magnetism interrelate. You also end up with a 4-vector potential. This is something you're going to use a lot in this, if you're trying to do electrodynamics in relativity. And that's going to include the scalar potential from electrodynamics, as well as the three more components, which are the vector potential. So the 4-vector potential has a time component, which would be the 0 or the 4th component. That's your scalar potential, and your spatial components are going to be your vector potential. Then you have your field tensor, which obviously you wanted to build up. That's Fij, and that's going to have, as time components, you're going to have your electric field, and then you're going to have a fairly strange thing for your magnetic field that I guess I'll see if he has a picture of the matrix. I call it a picture of the matrix, right? Oh, there it is. Okay, so this is your field. So he's using the 4th component as the time component here. You've got no entries on the diagonal for your electromagnetic field. And you'll see here on those time components you have your electric field, and in the spatial components you have your magnetic field. This is an anti-symmetric tensor, which means that these components on the opposite side of the diagonal are negative compared to the other side. Notice that there's kind of a weird sign convention in there. That's the way it works. And so that's how all of these things work together after you've put the 4-vector potential together and then constructed your field. So this is how your field looks in relativistic electrodynamics. And then it discusses the Lorentz transformations of these things, the Lorentz force, which is something you can pick up, and it's very important. This is really the connection between electricity and magnetism, the deep relativistic connection between them that says basically that they're the same thing. Then the energy momentum tensor for an electromagnetic field. Again, that's what's going to take the electromagnetic field and allow it to push things around. And then you go to general tensor calculus in Riemannian space. So basically that means, we were talking about fairly simple straight line coordinates. Here we're going to have coordinates that change at different spots. So that over here you might have your coordinates in, some nice reasonable seeming directions. Then over here it'll slowly change like that, or maybe like that, or something like that. So that the coordinates, whereas, where they're nice and simple over here, end up being in some sort of different position. So that's more or less what this is going to do. Generalized n-dimensional spaces, curved spaces, spheres, and hyperbolas and hyperboloids and strange things like that. Then you have to worry about the covariant and contravariant tensors, and again, this is a very important thing. The thing that I wanted to say is that although these are very important, and And he does give a good explanation for these, for covariant and contravariant tensors. He does so in terms of transformations, okay? If you're not really sure about that, if you want to think about it in the terms that I'm saying, where you're talking about how you're measuring things on the grid, Shadowitz's old book on special relativity, which I think is out of print. There was a Dover edition after this one. This is the one I found. Gives a really good explanation about that. Quotient theorem, conjugate tensors, covariant derivatives, parallel displacement, defined connections. If you have to understand the connection. You really have to understand the connection, and I wish I did. Transformation of affinity, covariant derivatives of the tensors, which are things you're going to use, obviously, when you're making these Christoffel symbols. The curvature tensor, we care very much about the curvature of space-time, and basically the curvature is 1 over the radius, right? So if I have a sphere or a circle, let's say it's a sphere that's got this as my radius, then you've got this curvature here, and that curvature is 1 over, you've got this curvature on the sphere, you see that here, and that curvature is 1 over the radius. But there's also a tensor associated with that, partially because it doesn't have to be the same in all directions. You need the connection, metrical connection, raising and lowering indices. This is going to be very important, raising and lowering indices, because you can only do a multiplication. Where did I do this? So if you'll notice, when I did this, I just used I and j. You can't actually do that in special relativity. You have to do something like this, A alpha, B alpha. And that's going to be your sum. Okay. You can really only add that way. If you have something like this, if you have A alpha, B alpha, to make it work, you need a G alpha or alpha. See, how would it work? Alpha beta, I think. Because you have to put a beta here. Because you have to change the, you have to raise this thing. So you need to use a raising index so that you can do these multiplications. You need a dual space, basically, right? Because these spaces like this, where things aren't parallel, they need a little bit of work. They aren't going to give you the same lengths as these unless you do something like raise and lower indices. Scalar products, magnitudes of vectors, same sorts of things, only now in this curved space-time. The geodesic frame and Christoffel symbols, Bianchi identity, again, things that I should have remembered. Let me see what my notes say about them. That's why I have notes. And I don't have anything for 39 or 40, so I don't go straight from 38 to 41. Usually what I do with these notes is I try to write a single sentence for each section. That's why I like books with large numbers of sections like this, continuously numbered, because then I can go for each one and just after I read it, write down a sentence that's basically the topic sentence for these 3 pages. Now, here I'm looking at this. This might be the reason why there's not one here. The Bianchi identity is like half a page or something. It starts on 111. The covariant curvature tensor starts on 111. It may have been a little bit light or just a whole bunch of math, so I don't remember. Divergence, Laplacian, Einstein's tensor, things you just need to get together. In fact, basically what all of this stuff is, what these 11 sections before this section is, this is all just working up to build the Einstein tensor. And like I said, when I took that 8-week course in general relativity over the summer. That's basically what the first 6 weeks felt like, is just building up to Einstein's tensor. And then we had 2 weeks of actual general relativity. And again, that's fairly similar to what this has. Then you get into your principle of equivalence, which is, I'm not sure which one he uses. The easiest one is all accelerations are the same. There are several different ways to talk about it, and it gets kind of technical. I think he only has the one. The metric in a gravitational field. So now we're going to add gravity to special relativity, more or less, and that's going to change how we look at things, basically through this principle of equivalence. The principle of equivalence is doing the same sort of theoretical work as the special principle of relativity did for special relativity. Right, this is the deep insight. On what page 127, section 44, this is the deep insight of general relativity. This stuff is building up the mathematics so that you can understand what that principle really, really means. Right? Then you have motion of a free particle in a gravitational field. Exactly what you want to know. Einstein's law of gravitation. The headline equation, basically. Let's see, acceleration of a particle in a weak gravitational field. Newton's laws of gravitation. Going the other way down to show you it works. A freely falling dust cloud. Metrics in with spherical symmetry. The Schwarzschild solution. Simplest solution to general relativity. Planetary orbits. Gravitational deflection of the light ray, gravitational displacement of spectral lines, Maxwell's equations in the gravitational field, black holes and gravitational waves. And that's where my general relativity text ended, or not text, book, or not book, class ended. We ended the semester with gravitational waves, although there was one more book on elements of cosmology. Then we go to the cosmological principle, cosmological time, talking about cosmology again. Spaces of constant curvature, which are sort of what they look at in cosmology a lot. And then they talk about the Robertson-Walker metric. The FLRW metric is basically the metric for cosmology. There are lots of metrics, but what I'm saying is that when you're looking at something, the Friedman, the Robertson-Walker metric is the big one, and that one encompasses all of sort of the other ones that you've looked at, like de Sitter space and anti-de Sitter space and so on, and yeah, and stuff like that. And the in between those two is the Minkowski space. So this is a particular space. I'm not it's been a little while since I've actually looked at it, so I don't recall exactly how he talks about it, but this is the metric that takes a positive curvature to a negative, and a negative to a negative curvature state with Minkowski in the middle. That's used a lot. Hopefully I'll finish another book and then I can come through and talk about 10 billion different kinds of metrics, because they're cool. They're all cool. Hubble's constant and the deceleration parameter. We talked about Hubble's constant. This is an old book, so we're not talking about some other things that we might talk about, like the cosmological constant. Maybe he does have the cosmological constant. I don't remember if he has the cosmological constant. He does. He has it in 137, so he talks about it for the acceleration of, no, it's either in 47 or 48, probably 47, talking about Einstein's law of gravitation. You can add in the cosmological constant right there, so he does talk about it there. He will talk about it later on. We talk about redshifts of galaxies, luminosities, distances. We talked about the Hubble constant recently on the podcast. That requires you to understand things like luminosity distance and redshift of galaxies. Talk about the cosmological dynamics. Then you have model universes of Einstein and de Sitter. Here we're getting into the lambda again and the cosmological constant. Friedman universes, looking at my notes here, that's exactly what I was thinking about here. Friedman models depict an incoherent dust cloud, predicts a cycloid that repeats bangs and crunches. So k equals 1 is the cycloid, k equals 0 is an open universe, k equals -1, that's the universe that expands forever that we think we have now. I think. Don't quote me on that. You can quote me on that. That's okay. Nobody's going to care. Radiation model. So we have a dust model. We also have a radiation model. Those are two different things. And the particle and event horizon. Okay. So this is a little odd because when I look at the radiation model, it says it's independent of the cosmological constant in my notes, but that would to me indicate that he talked about the cosmological constant and just didn't end up in the index. The index does have the cosmological constant in the exercises there on page 198. But that's all. So I did want to look at some of the questions in here. The first one is a warning. Well, I shouldn't say that. This is going to make me look stupid. But the first problem here basically has you derive the Coriolis force, and it's tricky, and it's not tricky because of the math. If you understand transformations, it's more or less physics 1 stuff. The thing is you have to be very sure what you're actually solving for. So if you're having problems with this one, just go on to the other ones. Okay, that's the most important thing. Because what you're missing there is you're either making an equivalence between the same thing twice, or you're starting a little bit early and or ending a little bit beyond that. That's a common problem. I had a problem for one problem or one example in E&M when I was teaching junior E&M. I had that problem over and over and over again, where I would always pass the point where I had to get to and end up trying to solve for something much more complicated. And I could have just stopped, done a substitution, and been done. Right, and that's more or less what you have to do here. There's a place where you just have to stop, do a substitution, and you're done. As you see, I think this first chapter is pretty light on questions. I think it's only 21. But when we come over here to, I'm not sure about, this one only has 17. I think this, yeah, here we go. This is what I was thinking about. Here we go, and we end up with, when we're doing the math instead, we're getting 72. This is the mechanics. We're getting 72 here. There were some other things here. I'm not sure about this one, but this is exactly the kind of thing that would be difficult. That one doesn't look too bad. Here we go. We have tangent of 1/2 alpha and tangent of 1/2 beta is equal to the ratio of the difference between the speed of light and the velocity of the object, and the speed of light plus the velocity of the object. These can be tricky. So there are several of these in the text. The physics isn't that bad when you're dealing with these. But usually when you see something like this, the trigonometry is going to be pretty bad. So if you see something like this, the most likely problem you're going to have is going through all that trig. And I know my students seem to love trig because when they could just apply some fairly simple principles and get an answer, they look for trigonometric identities and things like that that are highly obscure and sometimes don't work quite right. So again, sometimes you have these fairly short sets of problems for a chapter, and sometimes you end up with very large numbers of problems. So 35 here, again, that's a little bit too much. 20 is on the outside. 20 you can do all the problems and feel good about yourself. Over 30 and it's just, you just have too much to do. Probably. I mean, probably you're going to have the general idea of most of this stuff as you go on, in general, I think, for most people. And so you just have to choose between them. Okay, so that's the book that when people come to me from the podcast, I will recommend they use to try to figure out tensor calculus. I mean, if you're in a good program, then there should be a math methods for physics that'll have a lot of tensor calculus stuff in it. I do feel like I had 2 semesters of that as an undergraduate. I do feel like one of those semesters was all vector and tensor stuff. So that's what I feel like. I don't have the syllabi any longer or anything like that. Those disappeared in a move early on. So again, those books, they're probably pretty competent at it. They just aren't focused like this one is towards the relativity. And again, people do need a lot of that work on the tensor calculus most of the time when they're beginning. So it's something you have to get used to get an idea about what's going on with all of that. All right. Okay, so I mean, to end, again, if you're going to look at something like this, please do use the Amazon link to buy it. I'm trying to stay in the affiliates program. I don't sell a lot of these things. I don't really care to, but I want to keep those short links. So I want to have this nice little button that gives me a short link so I can send you these. So if you are going to buy something like this, do use those so I can do that. I mean, it's just much more convenient for me to be able to do that and for somebody to see that. I don't want to use a 3-line long link every time I want to recommend a book. So that's the only reason for that. Do I have anything else? There are a couple of books I want to talk about, but I do have to reread them because I read them before I was doing... I read them too long ago. There's at least one thing in there that I'm completely confused about and I don't really understand. But I'll put them down. I'll let those be a surprise. They're not that exciting, but it is nice to have a surprise now and then. Okay, so thank you very much for listening. I will talk to you again next week. Bye now.